So we've come now from the exhibition ground where we saw the 4 items of test equipment for testing materials, and we've come to the place where these are based. We've come to a place called AGE, which stands for Advanced Geotech Engineering and Testing Services, and this is in Thorry-Lamb. And so we're going to go inside and look at their laboratory where we can see more pieces of material testing equipment. And remember, we're talking about non-destructive testing. So let's go in and see what they've got here. Hello, Yang-Chen. Thank you very much for letting me come to visit you in your laboratory.
We are so glad you could come.
Thank you very much. Now, this is a bit of a change from the exhibition ground, isn't it?
Yes, sir.
But can you tell us who your staff are here?
She's Ms. Kezang Wangmo, electrical and electronics engineer, graduated from Sikkim Manipal Institute of Technology.
Right, very good.
He's Mr. Nima Tamang, who has 20 years of experience working in quality control laboratory with Bhutan Standards Bureau. And he's Mr. Budiman Tamang, an IT graduate from Orissa, civil engineer.
Civil engineering.
And
right?
Mr. Prakash Monga, civil engineer, graduate from Sona Technology College in Chennai.
In Chennai?
Yes.
Very good, very good. So this measures the shear strength of the soil. Now we better explain what shear strength means, hadn't we? Because not everybody knows what shear is. And so, you know, you've given some nice biscuits here. Let's use the biscuits to look at shear strength. If I take a pile of biscuits here, if you think about the strength of that pile of biscuits, let's say I was going to build a building on top of this pile of biscuits. I want to know, first of all, if I press down hard, how much force does it require to make that pile of biscuits collapse? So that's one thing, and that's the sort of thing these machines will measure. But if we're looking at this machine, it measures shear. And what shear means is this. Look at that tile of biscuits, it's vertical now, but if I exert a sideways force, it goes like that. So shear, the shear strength, is how difficult it is to make that pile of biscuits go whoop, sideways. Because if I've got a high shear strength, then it'll be very difficult. And this will be very good for my building, especially in an earthquake, for example, because even though the earthquake may be making the building wobble, if this is strong, it'll be okay. But if this is weak, when the building wobbles, it'll go whoop, like that, and the whole thing will collapse. So the shear strength measures the ability to withstand sideways forces, and that's very, very important in an earthquake, isn't it? Thank you for those biscuits. And of course, I need hardly say other things we could do about this biscuit. Something very important about this biscuit is how much force does it require to break the biscuit? And that again, if we're talking about building materials, the force required to break the material is a very important quantity, isn't it? Because, you know, if the walls of your laboratory here, if they were made of biscuits, then you push the wall, boom, the wall will break. So, that's the weighing machine.
This is the weighing machine?
Now, this is a plain weighing machine, and I invite everybody who's watching this program to guess. Do you mind being weighed, Yang-Chen? I invite everybody watching this program to guess the weight of Miss Yang-Chen here. And in England, there are people who earn money by saying, if I can guess correctly what you weigh, you pay me some money. So I'd like you to think, how many kilograms is Madam Yang-Chen here? Now, would you like to get on and show us? There we are, 51.8 kilograms. I wonder if anybody got it right. I'd like to be able to say if you got it exactly right, you could write in to the Royal Tutorial Initiative and you get a reward of 5 kilograms of pure gold. Wow. But that's not true. Now, what does this do?
This apparatus here is California Bearing Ratio, which is also called as CBR apparatus. This is again to study the foundation or the strength of the base before you construct the road, and that helps you to design the thickness of the pavement.
So, Yangchen, these to me look like lumps of chocolate cake. What actually are they?
So these are the core samples that we have extracted from the road which leads to the planned education city near Chunzom.
Yes.
We have extracted the samples to measure the level or the amount of bitumen that's been used.
Right, so the amount of bitumen in the road.
Yes, sir.
Yes, why?
This is done to ensure that the construction is according to the specifications laid down in the contract terms.
To make sure that the people who built this road have done what they said they would do in the contract.
Yes, sir.
Which is very good indeed, because if they haven't, and the road is not according to the specification, it can collapse, go into potholes and Lord knows what. Very good. Now, what's this thing in the corner here? We've got another machine here, a bit of a handle and a sort of a cylinder thing and a dial. So what does this do?
This machine is called the soil test apparatus.
So here we insert the soil sample in this cabinet, and also we pour some amount of water in the outer cabinet. And as the soil absorbs the water, the soil tends to swell, and as it swells, there is a force that's exerted, and this gauge reads the swelling property of the soil.
Right, so it says how much soil swells.
Yes.
When does the soil swell?
When there's moisture added to it.
So if we've got soil and it rains, the soil will swell.
Yes.
And so we need to know how much it swells,
Yes.
because that will determine whether it's suitable for putting a building on top.
Exactly.
So how does it work? Where do we put the soil sample?
We insert these samples in this place.
In there, in this cylinder,
Cabinet, yes,
right?
sir. And then we apply pressure.
By turning that.
Yes, sir. And
And
the
it
amount of
squeezes the soil in this cylinder.
Yes, sir.
Yeah. And
And then we pour water.
so you pour water inside
outer
there,
cylinder. Yes.
which makes the soil wet. The soil swells,
Swells.
pushes up on
Pushes
there,
up and-
and I don't know whether the camera can see, as we push up, the little needle there changes,
Yes, sir.
so we can measure how much the soil swells.
Exactly, sir.
All these interesting things about soil that when we just walk around and look at it, we never think about, do we? Well, now, can we go and look at those testing devices that you showed us at the exhibition? So before we go, actually, this looks interesting. This looks to me like something for cooking momos. What actually is it?
So this is sieve analysis apparatus.
Right.
These are sets of sieves that are arranged according to the aperture sizes.
Right.
And this is normally done to measure the thickness or the particle sizes
Right,
of
so
the soil.
particle sizes in the soil.
Yes.
So we've got sieves here.
Yes.
Now, if we can take that off, and if we look inside, we don't find momos, we find that. And if you notice, the holes here are big, but as we go down, can I, Yangchen, get you to hold that?
Yes.
As we go down, the holes get smaller and smaller and smaller and smaller and so on and so on. We won't go all the way down. So at the very bottom, we get the finest particles which have gone through all those little holes,
Yes.
and at the top we get the big things, the
Yes.
stones and things.
Yes.
So this tells us, if we take a sample of soil, it tells us what the soil is made of, how big the particles in the soil is. And that again is very important. Well, I'm so sorry. You could use it for cooking momos though, couldn't you?
No, sir.
If you put a boiling water under here and the boiling water comes up through there, be perfect for cooking momos. Let's go and see the things
That
we
would
saw
be
at the
efficient
exhibition.
use.
So, Yangchen, here we are. Here's some of the apparatus that we saw down at the exhibition ground.
Yes, sir.
So now, hello.
Hello.
Are you going to explain one of these to us?
Yes, we'll have Mr. Budiman Tamang explain the non-destructive techniques.
Right. Let's look at this magnetism one first. So just quickly tell us what it does and how does it do it.
It actually measures, finds the lever, locates the lever, metal inside the concrete. Sir.
So this locates the iron bars inside the concrete.
Yes.
And of course,
mechanism is electromagnetic.
so this works by magnetism.
Yes. Sir.
Right. And of course, the number of steel rods reinforcing a concrete column is very, very important. If there are not enough steel rods, it isn't strong enough to hold up the building. All you need is a little earthquake and the whole thing falls over.
Yes.
Now, I'm going to ask you to hold that.
Okay.
And I'm going to try and explain how this works. And in order to explain how it works, I'm going to have a little plastic jug and a wooden spoon and a length of wire. Now, if we look at this probe, what's inside that probe is a coil of wire, thousands and thousands of turns of wire, a little coil.
Yes.
I'm going to make a coil of wire. The difference is this is thick wire and I'm only making a few turns. But there's a coil of wire. Now, I'm going to pass an alternating current through this coil of wire. And you should know that an alternating current is a current that goes first one way, then the other way, then that way, and then the other way, backwards and forwards, like that. And, of course, it's changing direction all the time. Now, it's a bit like me taking this plastic bowl, putting some water in, and stirring it first that way, then that way. First that way, and then that way. Water in there. It's quite easy, isn't it? It's not very difficult. So, the current is going backwards and forwards in that wire. It's not too difficult, just like this. But if I bring a bar of iron near to this coil, the alternating current there induces eddy currents in this bar of iron, little electric currents in this bar of iron. That affects the coil, and it makes it more difficult for the alternating current to go backwards and forwards. It's just like if I've got water in this bowl, very easy to stir. But let's say I filled this bowl with Tate & Lyle's golden syrup, or with thick oil, then it's much more difficult to stir backwards and forwards, isn't it? So this is what happens. When I put a bar of iron near this coil, it becomes more difficult for the alternating current to go backwards and forwards. In effect, the resistance to the current flow becomes bigger. But because it's alternating current, it's not called resistance, it's called reactance. And so it becomes more difficult. And this box down here measures the reactance of this coil. So when it gets near an iron bar, the resistance of this coil to alternating current, in other words, its reactance, increases, and I get this showing up as a figure on this machine, so I can detect where the iron bar is. And if you had an iron bar in your go there, we'd be able to find out. So this marvelous device depends on simple principles of electromagnetism, electromagnetic induction, reactance, things you've learned about at school in your Class 12 physics syllabus. And we'll take this outside, can we, and measure in a minute? In a minute we'll go outside with it. And this, you'll remember, it works by ultrasound. So do you remember, we saw it in the exhibition ground, this gives out ultrasound waves, this detects them, and so you can measure the density of a concrete block. Have you got two concrete blocks we can measure? Right, one there. Right here. And one there.
So we have one here. It's highly compacted, so density is very good here. So, and here we have very light one. So we have very less density here.
So which one would I choose to build my 4-story block of apartments?
Dense concrete here, right?
The dense
This
concrete
one.
is better. Right. Can we measure it?
Okay. Right, we have this gel. We are providing on the probes. So
Right.
there will be a good transmission of the
Right.
sound between the probes.
So this is exactly what happens in the hospital, isn't it? If you have an ultrasound, they put a little bit of gel on your skin or on the probe, and that gives a good transmission of the ultrasound waves, which are, remember, are very high-frequency sound waves. It gives a good transmission from the probe into your skin. In our case, from the probe into the concrete. Can I get you to put some on? So we put that, a good lump of gel on there. That's more than they put on you, I think. And put it on both the transmitter and the receiver.
So I need some help for this.
And so we're measuring now how the ultrasound transmits through the concrete. And the ultrasound will go through differently if it is dense concrete compared with if it's not dense. What are we getting? We get a reading there. It says what?
This is the velocity of the sound.
So the velocity of the sound waves through there is 43.7 microseconds it takes to travel across. So it tells us how long it takes for the sound to travel across. And this is, you say, a dense, good concrete. Can we try not so good? So 43.7 for the good. Will it travel faster or slower in the bad, I wonder?
It will go just slow.
Ah, so it should go slower in the bad concrete. Let's see whether it does or not.
Okay,
Takes, oh. Well, it's going at, it takes 58.8 microseconds compared to 47. So it takes longer to go across here, therefore the sound is travelling slower. And this tells me this has got lots of air pockets in it and it is not very strong. However, I did notice, you know, when we came in, I saw these 2 blocks on the floor. Could you just put them on the floor for a minute? So there's another way of testing density which occurred to me when I saw them on the floor, because both the blocks are the same size, so the more dense one will have a higher mass. It will weigh more kilograms. The not so good concrete with air in it will be less massive. Well, I can test the massiveness using a very simple piece of apparatus called my shoe. And if I kick the very dense one, it doesn't move very much. But if I kick the less dense one with the same force, it moves much further. So, Yangshin, in spite of all your expensive apparatus here, I could have told you the moment I walked in with one kick of my shoe which of those was denser than the other. But of course, whilst that might tell me one is more dense than the other, it doesn't give me any figures. It doesn't give me values. And if you actually are going to build large buildings, you need to know exactly how dense the concrete is.
Yes.
My shoe wouldn't be very good if I was going to build a 5-story apartment block.
Right.
So that's why we have expensive apparatus. Now, can we go out and use some of these things? You may remember down in the exhibition ground we saw this thing here, looks a bit like a rocket, and this measures the
compressive strength of the concrete.
The compressive strength. Remember, this depends on Newton's laws. And so let's go outside and test something, shall we?
Yes, sir. So we'll go to the designated site.
Right, so Yangshin, what are we going to test?
This way, so we are going to test the structure, old structure here.
Right, so about how old is this building?
This would be around 20 to 25 years old.
Right, 20 to 25 years. And do you know whether it's good or not?
No, sir, we have to test.
You will test it, right. So, what are we going to do first?
We are going to check the location of the rebars and the diameter of the beams.
Right, so we'll check the location of the iron bars and
Yes.
see how many there are there.
Yes.
How many would you expect there to be in a column like this?
2 to 3.
2 to 3 at
Yes,
least.
at least, yes.
So, where's the man with the magnetism tester?
It's like CT scanning the building.
It's just like CT scanning. Because, you know, when you go for a CT scan, they don't have to cut you open to look inside,
Right.
which would not be very nice.
Yes.
They can actually see what's inside you without cutting you open using X-rays.
Yes.
Now, here, instead of X-rays, we're going to use magnetism.
Without
so-
causing any damage
Right.
to the structure.
We're not going to knock down this beam to see how many iron bars there are. So as the scanner is moved along the column, the figure we see here tells us how deep it's looking into the concrete. And when it comes to an iron bar, we get a little beep. So you heard the little beep, that means there's an iron bar there. So there appear to be 2 iron bars in there, and if we come along here, we get 2 iron bars as well. So perhaps here there are just 2 iron bars. Nowadays,
It's
We-
2 bar in one face,
2 bars in one face.
one face of the column.
Right, so 2 here, so 1 there, and then further in, so 4 bars.
Four bars.
So we've got 4 bars altogether here, which is a bit better than 2, isn't it?
Yes.
Because if there were only 2 bars in this pillar here, it wouldn't be very, very strong. But we're able to see all that without breaking up the column, just by magnetism going inside and detecting an iron bar. Let's have a look at that.
Okay, it finds the compressive strength of the concrete.
Right, the compressive strength. In other words, how much compressive push force I can put. And if you think of this structure up there, it's all pushing down. All the weight is pushing down on here. So the compression strength is very important. So just tell us what you're going to do.
Okay, I'm going to hit this structure
Right,
with this thing. So it gives me a number.
right.
So we, from that we find the compressive strength.
So when this thing hits the concrete, it's a bit like hitting it with a hammer, and we get a rebound, we get a reaction, and this measures the reaction, which tells us what the compressive strength is. So let's have a look and see.
So I got the reading here 25.
Right?
So we look to this graph.
We look on the graph.
So the strength of this structure would be 180 kg.
Which,
180 kg per centimeter square.
per square centimetre. So what that means is 180 kilograms per square centimetre. So if I were to take a square centimetre of this concrete, it would hold up a mass of 180 kilograms.
Yes.
So if I measured the area of this column, I could calculate quite easily what the total mass, how many kilograms this column could support. So this is a very easy and quick way of seeing how much building this thing can hold up. If I wanted to build an additional floor on here, you could measure that and say whether this was strong enough to
hold.
take the weight of an additional floor. Also quickly, and you didn't have to knock the building down to test it. Very good, thank you. So this, remember, is all about non-destructive testing. And it's exactly like, as I mentioned earlier, what happens in the hospital when you go for an X-ray or you go for an ultrasound. The X-rays and the ultrasound can go inside and they can measure things inside your body without cutting you open. And non-destructive testing of materials for buildings can measure what's inside, how strong it is, without actually cutting the building open or knocking the building down. So thank you very much indeed. And so if any of you want your buildings non-destructively tested, or you want to know how strong the soil is you're going to put your foundations on, remember, physics comes to your rescue and allows you to carry out non-destructive testing. Thank you very much indeed.
Thank you, sir.
So physics is very useful. Yangchen, thank you very much indeed for showing us your advanced geotech engineering and testing services. Now, the building that we've just looked at and you've just quickly tested is about 25 years old.
Yes, sir.
When this building was built, there were no testing services,
no
were
testing
there?
services.
But now, today, the rules are stricter and there are testing services in Bhutan. So,
Yes, sir.
do lots of people come to you for testing services?
We have been struggling to create greater awareness about the importance of quality control and assurance
Right.
for the construction activities in Bhutan. But recently, with the Ministry of Works and Human Settlements having put this testing to be a mandatory on the contract terms, we are slightly better in getting few works or jobs to
Very good.
test.
So it's often the case, isn't it, that, you know, if I'm going to build my house, I'm not too keen to spend money on testing services unless I have to. So do you find sometimes private contractors only come to use your services when somebody says, hang on, we're not paying the bill?
Exactly. So we have faced some situations where contractors come to us at the last moment when their bills are held up by ministries,
Right.
governments.
That tends to be human nature. But of course, when you're building a 5 or 6 story apartment block in which a large number of people are going to live, it's very important that it's safe, isn't it?
Yes.
And what we've tried to show in this program is that physics contributes towards building a building which is safe and secure for your family to live in. And you need to, are you certified here?
Currently in Bhutan, we do not have anybody who can certify us, but we are hoping that Ministry of Works and Human Settlements or Bhutan Standards Bureau would certify us in near future.
Right. So this is an important part of the chain, isn't it? The government makes laws and rules about building safe buildings. The contractors have to implement those rules. You test materials according to the rules, but you also need official government certification
Yes.
so that your testing certificates are valid and accepted. So
Yes,
there is
sir.
a series of actions in that chain that have to be carried out. Well, very good luck. And again,
Thank you, sir.
it shows, doesn't it, how physics, the simple physics that you learn in school, can be so useful for looking after our safety as we build bigger and bigger buildings in Thimphu. Thank you, Yangchen, very much.
Thank you, sir.